It will start in 3, 2, 1. Hi,
Okay.
everyone. Welcome to this talk from Christian Pretorius. Christian is the author of Barch, a distributed key value database, and he will talk about Barch. And I will not do some stupid blah blah blah, and I will simply leave the word to Christian.
Thanks. Thanks, Federico. Yes, so Bark started as a project with some of the issues known at that time with remote and distributed caches. Like, as you know, I'm not sure if anybody can see the slides. I just want to know if people can see the slides.
No, actually, we don't see your slides.
Oh,
Have you
sorry.
uploaded them?
Yeah, I did upload them. I just don't know how to.
You should click on the share button, share options.
Hmm. But I'm not sure where to share. I'm on the same.
If you put
Yeah.
your cursor in the lower part of the video, you will see three
Oh,
buttons.
oh, there. Okay. Yeah, there we go. Ah, thanks. Okay. So there we go. We've got. So this is a project I started about 7 months ago for Barch. It's sort of a allusion to architecture and binary, and also there's this course called Barch, which is the architecture course for architectural students. It's just a little bit of a mix-up name. So when I started with Barch, or as you know, as my career progressed, I saw some of the issues with current key values or in-memory key value stores like Redis and VALKEY, which are primarily used for caches. So you can see single-threaded. They've got synchronous operation. A lot of the analytical data structures were of logarithmic complexity, usually to some kind of binary tree or derivative of a B tree or something like that, especially with order structures. Obviously, hash tables and so on is not logarithmic, that's constant time. And there was also a lot of focusing on the client server type architecture. So the cache only lived as a service somewhere remotely. It didn't, the architecture as a whole didn't consider the client as well. I'll go into that a bit later. And obviously, we have like stored procedures which are usually only run on the server. So that would also introduce latency. And then from a cloud point of view, we've got some inflexibility because of the way the replication is set up. And also the caches or the key value stores don't sort of mix well. There's always this impedance mismatch between the cache and the actual code that runs stuff or that retrieves or stores data on the on in the cache itself. And then there's elasticity. Now, with this, we're talking about uptime and SLA agreements and that type of thing, uptime, um, uh, redundancy, reliability, that type of thing. And a lot of this is one of the things that's problematic is the startup time. When you want to, especially with elasticity, when you want to create more instances very quickly and then shut them down very quickly, that type of thing. You don't really have a lot of time quickly replicating an instance. You want it to be up as soon as possible so that load balancing can kick in, that type of thing. Okay, so the next thing, so first I'm going to do just this sort of boring, just as a starter. We've got Redis and VALKEY to a large extent is single-threaded, which was a conscious design choice by the authors of Redis because they prioritized real-time responsiveness, and they wanted to make sure that the latency is as low as possible. However, this single-threaded design, or let's call it a single-sharded single-threaded design, has a few side effects in that you have to make, if you want to expand the cache or increase the performance and scaling, you have to do sharding with replication, and you also get the side effects of network write amplification. In other words, because you have to because if you shard, you'll have to break up your requests into per shard request, so one request becomes many, so you get a degree of write amplification depending on your MTU size on network. Oh, crappy. I'm sorry. So it can be solved, but it costs a lot of money because you have to fully replicate a whole server, so that any rogue packet can hit any server, and that yeah, there's obviously a lot of memory that you have to replicate. And just as an aside, Barch also uses internal shards, but I'll get to why that is a bit later. Here we've got a sort of the cake problem. We've got a single request on the right-hand side, gets the pipe. Okay, so first I have to just get a overview of pipelines as it's understood by Redis and Redis compatible caches. As the Redis client receives queries from threads inside of its client process, it will firstly not immediately send every request. It sort of has a clock or a bucket that it's like a conveyor belt type of thing, and then it catches every request into a bucket. So many times, because there's so many concurrent requests, you'll get a couple of requests that goes into one bucket, and that bucket is then converted to a big request, which is then sent to the caching server, and it replies also in a big bucket of responses. So that cuts down on a lot of network overhead. There's not only the write amplification, which I talked about, there's also the kernel switching which takes place. So you're saving on a lot of kernel switches to retrieve the data from the network card and then into the calling process and so on. So there's a lot of CPU overhead that gets saved because of this pipelining type of thing. But because you're sharding now, so your sharding architecture can take sort of two forms. The one form is to have a complete, well, let's call it a hash per hash value. So every key will hash to a certain shard. So that shard will only contain keys that hash to that specific value, like 1, 2, 3, or 4, or 5, or whatever. Or you can have many shards that contains all the data. Then you don't have to slice up your pipeline. But obviously, so you make a pipeline and then you have to slice it down again to go to the correct shard, or you have to have these huge shards with all the that uses a lot of memory to store all the keys and values. And that's why things like Dragonfly DB does so much better, is because they don't have to shard, or they don't have to slice up the. There's only one server, but every shard runs on a different thread, which shares the same data underneath. So then you don't have to slice up the pipeline into however many shards you've got. And there's obviously shard memory amplification. If you have multiple processes running, it also adds to the memory overheads. Okay, so in Barch, we've got a kind of a, okay, let's go back to this one. Okay, in Barch, we've got a sort of a similar architecture than Dragonfly DB, except we've added some asynchronous, some asynchronous libraries so that we can better split each thread. So when we do a single operation like retrieve from memory, we immediately queue that operation into a ASIO queue or asynchronous IO queue, and then we sort of break up each request read response cycle into several pieces, and then you can get much better or much smoother performance per thread. So basically, lowers your latency per thread per request. Okay, so now, when I started Barch, we had this. I knew about the art or the adaptive Radix Tree already. There was a paper written in 2012 about it. And it's also used in DuckDB and Postgres as well as a method of purification. It also reduces memory use because some parts of the keys are not the values, but parts of the keys are compressed. It also has constant time performance, although that's a bit difficult to understand since it's a tree. But it doesn't do any binary searches across the tree. There's only constant time lookups, and let's say for a tree with a maximum of 8 bytes per key, keys with 8 bytes maximum, you'll only ever do 8 comparisons, where a binary tree is like, I think it's, anyway, I think it's about 64 comparisons, 2 to the power, okay, and then of course the art gives you audit access while also having constant time. And another thing which I didn't add here is the hash tables has a tendency to a rehash. You do have to do a lot of rehashes as the hash table grows, which Redis solves by having a primary and secondary hash, one which you write to and another one which is sort of a replica. Or the secondary hash is a replica of the first one, and it doubles the amount of memory that it uses. And then also to get audit access in constant time, and there's a lot of interesting things you can do when you've got audit access. So if you look in Barch, we've changed some of the implementation details around the art in terms of how it is stored in memory. Like it says here, there's a method known as pointer swizzling, which they use within OR trees where they use the one or two of the most significant bits in an address to indicate whether it's another page or or a leaf value, or the pointer is actually a pointer on disk somewhere. But in Barch we don't do that. We add another byte per key, and in that we set some bits which tells us which where the destination page lies. So we can increase the usable address space and also have a lot of extensibility on where we want to put these pages. Maybe we want to put some in disk. Maybe we want to put some far away and remote places. But anyway, so we've added some bytes. So we need to make the bytes a bit, pages a bit, remove them again. And we do this by using offsets and 32-bit pointers instead of 64-bit pointers. So we have a allocation clock. So there's a special allocator for art pages or art nodes, really. This allocation clock pre-allocates some address or reserves an address every 1 million or so allocations, and then you can use that address as the offset for the following allocations, and then you can just subtract it from the address you get from the allocator, and you be guaranteed a much smaller address which doesn't conflict with any other null addresses or things like that. So basically we've used 1 byte per key, and now we've taken 4 bytes off again. So we're saving about 3 bytes per node, or 3 bytes per key per node over traditional OR trees. Okay, so in this implementation of the OR trees, we also have a accumulator, which stores the total count of value of keys beneath it, not nodes, just the total amount of leaf nodes. And then as you traverse the tree, it remembers the traversal path as a stack, and then at the end you go back in the stack and add 1 for each key you've added during that traversal. Usually it's only 1 or 0. And then of course on the removal it subtracts 1 again. So you've got so each key in the stack is bigger than the keys beneath them, or smaller than the keys beneath them. So the top of the stack has a key as a leaf pointer, and the one beneath it is an internal node with a count, and then the one above it is a count bigger, and so on, until you reach the root, which contains the total amount of keys in the whole tree. So how we can use that to do fast sums, fast ranks, that type of thing, is I've got a little picture here. So this picture sort of shows the 2 traversals of the words bad and big. So you can see in this very simplified art diagram or tree diagram, you can see that the root node, the total size of the tree is 125, and each node within this tree only has 5 subnodes or child nodes until you reach the leaves at the end. And you can also see there's a little green part that's measured 25. So now you can, so basically the process is then to first traverse. So we've done so after a lower bound, we have 2 stacks, basically, like I tried to explain before. one for bad and one for bed. And you can see already that there's at least 25 between the word bad, or 25 times 5, so there's at least 100 between the bad key and the bed key in this simple example. Okay, so for startups, we need to get away from the idea that you need to logically insert keys when you on startup. So we have to act a bit more like a database and use the pages directly within the database. And we do this by virtualizing the art nodes, as I explained before. We also have multiple shards, and each shard can load up concurrently with all the other shards, while not having to logically add any of the keys to the internal data structure, which is different than the way Redis and VALKEY does it. Some of the other ones like Garnet doesn't even do that properly. You're kind of on your own if you want to load the thing up. So in Barch's case, the startup time is limited more by the I/O and less by the CPU, and the physical format is still relatively small, which is an advantage of the logical key scenarios where the size of the database basically is fairly small within things like the whole key. But it doesn't help because you have a single threaded CPU, which is adding a lot of logical keys into the hash table every time it starts up. Okay, so the next thing is we want to reduce the latency as far as possible, and of course, network is the last barrier to latency. We've sort of cut down everything else. Now we need to cut down on the network itself. And the way we do it in Barch is to create sort of local nodes, which are also participating in the global, or in the system-wide cluster. So these local nodes can be replicated to and from. That can become fully functional nodes within the whole system. And in this case, we're using Swig to generate interfaces for different languages. Currently, we only have Python, but things like JavaScript, C# would be finished soon. And we can also have interesting architectures where we can make the local caches small, let's say 64 megabytes, and then add a LRU, or set up the LRU to evict some keys while it caches the most used keys locally, and then on the on cache misses, it will request the keys from remote servers which have much larger caches. So that way you can remove a lot of load as well as latency from queries and from the servers themselves. Dragnet. So because we have this virtualized physical image of the database that we use, we can also quickly synchronize between servers when you've got a new node starting up, and you don't have to synchronize. You also don't have to necessarily synchronize. You can just start a new node. And there's some routing logic for that, so that the new node, while it's not full of keys yet, it can actually route some of the queries to other nodes which do have all the keys, so they can become, so eventually once they're full, they will once they're full, they will stop routing, and then you will have a fully fledged node. So it's kind of like leeches in BitTorrents. Okay, so now we're going to talk a bit about the hash table, even though I said Barch is ordered. It does have a hash table which you can configure, but we did it a bit differently here. We've got a primary and secondary hash. So the primary hash is very simple. It only contains the key and 1 bit for each position in the open address table. You usually have 2, which is the existence bit and the what's that thing? I forgot that word. Sorry. Yeah, the first and second. The second bit is the sort of the date. It marks a tombstone. Yes, that's what it is. It marks the tombstone of a previously deleted key. But in this case, we only have the 1 bit which marks existence, which has some interesting. It has some drawbacks because you then need a secondary hash to handle the collisions and erasures, because if you erase a key, you still have to probe all the way. But because we have this primary and secondary hash, we can make the probes very low, like 4. We never probe more or less than 4 on the primary hash, and then the secondary hash doesn't even need to be a hash. It can be a red-black tree or ankle hash or art even, which makes this hash somewhat resistant to hashing attacks or collision attacks. And yeah, it also gives us another interesting property in that we can improve the speed of rehashes as well as loading. So during a rehash or a load, and we know all the input keys are going to be unique, we never need to actually compare or make any comparisons in the primary hash. We also have another variable called well, it's basically a value which gives the maximum size or the maximum ratio of the secondary hash. So we can say the secondary hash may never be larger than 5% of the primary hash. So we know at least 95% of the queries to the hash table will end up or terminate in the primary hash. Okay, then to carry on, yeah, so like I said before, during rehash, we then 95% of the keys doesn't need any key comparisons. We only have very fast bit comparisons when we need to find a spot in the hash table for a new key. And of course, the probes are low, so we never, let's say the probes are 4. I think they are 4 actually. In Barch, it means that the rehashes as well as loads are much faster than a normal hash. We also use, again, we use offset pointers to the keys. So that means you can have a hash and the art pointing to the same keys if you want. But currently I've switched that off. We can either have a hash or an art. You don't mix up the two, just for simplicity's sake. Okay, now we've come to the thorny issue of memory safety. So within Barch, we do several levels of memory checks. There's the usual one where we do like subscript operator array memory checks to see if things are, are as they should be, so that we can guarantee that we're not going past memory. Then we also have within the virtual memory, which where all the keys and nodes as well as keys for the art is stored. We also have a use after free check table, which is basically just the free space table. And then those tables, those hash tables, which stores the free space and those type of structures into the virtual memory themselves have address checks and some address checksums and stuff, so that you can't also have, well, I wouldn't say it guarantees memory safety, but it makes it very hard to do use after free or double delete or memory overwrites at runtime, and it's always on even in release versions. Some future additions I would like to get finished at some point is named key spaces. I've talked about the different kinds of data structures that's used for the APIs within Barch. So I would like to have like named key spaces for a hash and named key spaces for art. And both of them would be sort of separate but still within the same address space of the process. Obviously encryption in SSL, then of course asynchronous user messaging. So maybe we can add a sort of structural API where we can store hierarchical structures, and then you can, when you insert the structure, let's say it's a temporary node, the changes will get replicated to clients as well as servers everywhere. So then you would be able to use Barch for a kind of a interprocess or server-to-server communications protocol. Then it's also per key compression. I was thinking about a thing called FSST, which you also use in DuckDB, or the normal Z standard can also be good because it also supports dictionary compression. Okay, so here's some examples. So we add some cats, eyes, and cars, and then we can do it either via the RESP interface, or we can do it via the VALKEY module. So Barch can also run within VALKEY. It can run within VALKEY. It can run within a standalone process. It can also run within something like Python. I've got a demo on the website or on Barch GitHub where it runs inside a Flask container, so they can directly access the cache from a Flask container to get that latency reduction. So here we have like 3 sets, and you can sort of naturally then do queries like this. For instance, I want to know how many cars there are. Then I can use this special count function, which you don't get in normal Redis, which will then give you these 3 cars. Same thing for manufacturer, 3 manufacturers. And then let's say bicycle, mountain racing, tricycle, via the range query. And then you can also mix them a bit, so you can use it for prefix lookups, and well as prefix lookups, as well as um, analytical queries. In this case, I just made a range on cars, or things starting with car or cat. So that will give you 6 like that. And this is some Python examples. So that's how the Python interface look. It's a bit more natural than the normal RESP interfaces. And then you can also set up remote targets within. So this first example here shows how you can set up a key value store within the local process. So all these keys 1, 2, 3 will be stored within the local process, and then you can also use the same interface to easily connect to a remote. And then you can also copy, so you can program your own replication scheme and that type of thing within your own software that you want to use to be a bit more flexible. And then there's some other interfaces which are also implemented, things like the hash set, the order set, and list. And these are the ones that they act, as far as I know, they act exactly the same as the ones that you've got in Redis and VALKEY. They've got a hash set, the order set, and list, like I said before. You can, yeah, and then you have all the sort of nice to have functions in Python. And then, yeah, that's it from me. I think I went a bit too quickly. But yeah, that's it from me. Some of the other stuff I haven't touched so much on is I think the way the memories is set up. So we always use for the keys, for the data itself, we always use a contiguous memory address space. And things we can do with that because it's virtual memory. You've got mmap functions in Linux and that type of thing. And you can also use it for Barch has the potential of being a normal database as well, so that you can have like a mixed version. So some of the memory is on disk, some of the memory is actually in memory. But we'll get to that eventually. And yeah, so any questions? I mean, or any questions or problems that you have?
It was a great talk.
Yeah, thanks. Thanks. Yeah, it's been a while. It's
Very,
been a while.
very in-depth and very interesting, especially
Okay,
for
thanks.
developers, I guess, because for
Yeah,
other people it could be very difficult to follow. Um, at least for me, some parts are difficult, but it's very interesting.
yeah. Okay. Cool. Thanks.
Um,
Yeah.
yes, please. Let's see if
Okay.
there are questions from the attendees. Um, I have only one actually.
Mm, mm.
You mentioned that Redis is single-threaded, and you don't seem to like this choice. Well, actually, most people don't like this choice. But
Yeah.
but I was curious if you actually made some tests to check if a single-threaded architecture without logs vs a multi-threaded
Okay.
has differences.
Yeah. Okay. So, yeah, the test we did. I mean, so I've got some things on the website, and some things I've done recently. So if we take hash table to hash table comparison, then you get about on my machine and on a AWS uh, 4x large, you get about the same speeds. So for Redis or VALKEY, which is a bit faster than Redis, you get around 1.5 million requests per second. While with Barch, you can get between 7 and 9 million requests per second. So And that's not actually, Garnet gets about the same thing. Garnet also gets about 9-10 million requests per second. So yeah, you can definitely do better. I think the initial issue with Redis, or that decision, was because of I'm not sure. I'm not sure why they don't sort of have in-process shards. That's actually why I think it became difficult to share the memory between threads. In Barch, we use there's something I missed. Uh, that's weird. But anyway, I had some. Oh no, not that. I think I must have skipped something. Oh, it's unfortunate. Yeah, there is some stuff I missed, unfortunately. Yeah. Okay, let's go back to the multi-threaded stuff. So in Barch, for every shard, you've got a shared lock as well as a unique lock during writes. And then there's a queue as well, because if you do a lot of writes, random writes to the same, from different threads to the same shard, then there's a lot of friction between. So by friction, I mean there's a lot of thread thread contention, which basically is, I think it goes deep into the Linux um, scheduler, or they've got that new completely fair scheduler in Linux. So every time you have a unique lock or two locks trying to get to the same um, mm, uh, into the same mutex, it actually goes into this complicated fair scheduler logic within Linux, and that takes up a lot of CPU time. So to resolve that, or to remediate that at least, is that we put it in a queue where the queue only locks for a very small time, um, and then it gets dequeued by all write requests to the same shard gets dequeued within the same thread. So then you never have this contention. So that improves the overall performance quite a bit. And then there's some other semaphores and things to make the latency less. So there's always a bit of a trade-off. You do have some latency because you're using these locks and you have to do all this queuing and stuff. There is an increase in latency. But at the same time, there's also an increase in throughput, which is good. Increase in latency is not good, but it doesn't increase too much, while the increase in throughput is definitely good. And the other thing is that the latency, because of the complete, I think in those days they didn't have the fair scheduler in Linux, and so everything is given, every running thread or every contentious part of your code is given um, uh, equal time within the kernel. So that makes it makes it much smoother. You have much smaller chances of a long wait for a request. So I think in the days when Redis was designed or coded first, they didn't have that nice scheduler that Linux has now, and so we have a bit more leeway these days because of the improvements in the Linux scheduler, which I didn't have at that time. So I think that was the reason for the initial design thing. And I also have these things like IO earring, that type of thing, which also is completely lock-free. It's not like EPOL, which we used to have in Linux, which there's still some locking happening on that thread. So when you receive network packets, but these days all that stuff has been sort of either improved by a lot, or they've been completely removed by newer interfaces and newer kernel drivers like IO hearing. So yeah, I think that's mainly the reason why Redis is the way it is because of the old limitations they had on Linux, and obviously there was a lot of older hardware. The hardware itself had a lot higher penalties for cache misses, that type of thing. I mean, this is as efficient accessing memory and that type of stuff. Yeah. Okay, that's as much as I know. I think there's people that know a lot more, but that's about as much as I know currently.
No, I think it was a great answer. Let's see if someone else has any question, but they didn't ask anything right now.
No.
Okay, so let me just remind people about the next talks. So in 15 minutes, sorry, let me check. On stage 1, we will have efficient data handling in cloud databases by Greg Kemlins, which is one of the original authors of Postgres and currently works at Wildkite. And on stage 2, we will have exploring ClickHouse as a unified telemetry database by Josh Lee, open source advocate. So you can choose which talk to see in 15 minutes. So for now, I will just thank Christian for his amazing talk and all the attendees, of course.
Thanks, Federico. Glad to be on this new Database Frontiers conference.
Thank you very much, and we're happy to have you. Okay, see you in 15 minutes to the next talk.